Good day, dear viewers. It's a pleasure to see you again on the Between Sleep and Science channel. In the realm of physics, there exist two grand pillars of law. One governs the largest structures in the cosmos, the stars and galaxies, known as general relativity. The other reigns supreme over the infinitesimal world of atoms, quantum mechanics. These two systems rarely interact, but there is one specific region in the universe where their rules clash head to head, the event horizon of a black hole. For decades, scientists believed that the black hole was the ultimate safe. Everything goes in, nothing ever comes out. But in the 1970s, a theoretical catastrophe unfolded. Calculations demonstrated something impossible. The safe was leaking. It turned out that black holes radiate energy, implying they have a temperature. This single discovery nearly shattered the foundations of modern science. Let us explore how a simple, elegant formula forced us to entirely rethink the laws of thermodynamics. If these quiet wanderings bring you even a moment of calm, feel free to leave a few warm words, or tell us in the comments which city you're watching from, so we can see how far our explorations travel. You can also simply like and subscribe. Your support helps other weary hearts discover this cozy corner. And now, you don't need to do anything at all. Just settle in comfortably and let the slow, steady rhythm of deep time gently carry you away from your worries. Let the journey begin. We must begin our journey by examining how physicists perceived the universe before quantum mechanics introduced its inherent chaos. We need to rewind to an era of pure reason and geometric clarity, a time when the black hole was not a paradox, but a mathematical ideal. To truly grasp why the discovery of a black hole's temperature caused such profound shock, we must first construct in our minds the classical black hole. When I refer to a classical black hole, I mean an object existing solely within the framework of Albert Einstein's general relativity, entirely untouched by any quantum effects. Imagine perfect darkness. Not merely the absence of light because you flipped a switch. In a darkened room, walls still reflect invisible thermal waves. There is air and life. No, imagine darkness endowed with mass. Darkness so dense that it fundamentally warps the very fabric of reality around it. The history of this concept predates Einstein by many years, stretching back to the late 18th century. There was an English cleric and natural philosopher named John Michell. In 1783, he posed a question that many at the time considered a simple, amusing thought experiment. Michell understood that any celestial body possessed a required escape velocity, the speed an object must achieve to permanently overcome gravitational pull and fly away. For Earth, this speed is about 11 kilometers per second. For the Sun, it's hundreds. Michell took his quill and paper and simply calculated how massive would a star need to be for its escape velocity to exceed the speed of light. At the time, following Isaac Newton, light was believed to consist of corpuscles, or particles. Therefore, gravity should affect them just as it affects a stone tossed skyward. Michell concluded, if a star with the density of the Sun were enlarged by 500 times its radius, its gravity would become so monstrous that even light could not escape. A ray of light would rise, slow, stop, and plummet back down like a ball thrown too weakly. Such a star, Michell wrote, would be invisible to us. It was a stroke of genius and astonishing foresight. But for a long time, it remained merely a game of numbers. The true physical reality of black holes only began to take shape in 1915, when Albert Einstein published his general theory of relativity, and everything changed. Einstein demonstrated that gravity is not a force pulling your feet to the ground. Gravity is curvature. As the famous phrase by John Archibald Wheeler goes, mass tells space-time how to curve, and space-time tells mass how to move. This phrase perfectly captures the essence. Yet, here is the surprising thing. Einstein himself was initially skeptical about the existence of black holes. The solution to his equations that described such an extreme structure was not found by him. It was found by a German astrophysicist, Karl Schwarzschild. The circumstances of this discovery were inherently dramatic. Imagine the year 1915. The Great War is raging. Dr. Schwarzschild is serving in the artillery on the Russian front, calculating artillery trajectories. Around him is the roar of cannons, mud, cold, and death. But during breaks between battles and suffering from a severe autoimmune skin condition that would ultimately claim his life, he was solving Einstein's equations. In these inhumane conditions, he found the first precise solution for a point mass. Schwarzschild sent a letter to Einstein from the front, containing lines like, "As you can see, the war has been kind enough to me, allowing me, despite heavy fire, to fully immerse myself in the world of your ideas." What did Schwarzschild find? He discovered that if you compress any mass down to a certain radius, which we now call the gravitational radius or the Schwarzschild radius, the space around it twists in such a way that the path outward geometrically vanishes. Let's try to visualize this. It is crucial for understanding why such a hole must be absolutely cold. We often illustrate space as a flat sheet and gravity as a funnel into which marbles roll. That's a good analogy, but incomplete. In the case of a black hole, that funnel becomes infinitely deep, but the most terrifying change happens to time itself. In general relativity, space and time are unified. Near massive objects, time flows more slowly. At the edge of a black hole, the event horizon, time for a distant observer appears to stop. Imagine you are watching your colleague fall into the black hole. You will never actually see them cross the line. You will see them slow down. Their movement becomes smoother, as if in extreme slow motion. The light they emit will become redder and dimmer until their image simply freezes and dissolves into the darkness. For you, they fall forever. But for your colleague, the journey is over very quickly. They fly past the event horizon without noticing any barrier. There is no wall, no stop sign. But as soon as they cross that invisible line, all possible paths of their future lead only to one place, the singularity at the center. For them, trying to climb out becomes equivalent to trying to return to yesterday. It is geometrically impossible. Inside the black hole, the direction toward the center becomes the direction in time. You cannot stop moving into the future, so you cannot stop falling toward the center. And this brings us to the main subject of our discussion, temperature. In classical physics, before the 1970s, a black hole was viewed as an object with a temperature of absolute zero, 0 Kelvin. Why? Let's use simple logic. What is temperature in everyday terms? It is a measure of the chaotic motion of particles. Atoms in hot tea dash around frantically. Atoms in a piece of ice merely shiver lazily. Heat is the energy a body can radiate in the form of photons. Light. Any heated body glows. You glow in the infrared range. A red-hot poker glows red. The sun glows white. This is called thermal radiation. But what is a black hole in the classical sense? It is an ideal absorber. It is a body that absorbs absolutely everything that falls onto it: light, matter, and radiation. Not a single photon can bounce off the event horizon. And according to the laws of thermodynamics, known since the 19th century, there is a rigid connection between a body's ability to absorb and its ability to radiate. There was a physicist, Gustav Kirchhoff, who introduced the concept of a perfectly black body. This is an idealized physical object that absorbs all radiation falling on it and reflects nothing. But the paradox in thermodynamics is that a good black body, when heated, must also be an ideal radiator. The sun, for instance, is almost a perfect black body for physicists, not because it absorbs light, but because it glows intensely on its own. However, a gravitational black hole is fundamentally different. It absorbs everything, but emits nothing. Absolutely nothing. Recall how the event horizon works. For a particle of light to fly out, it must overcome gravity. But inside the horizon, space is curved so that outward simply does not exist. This means no thermal radiation can escape the hole's confines. If an object emits 0 quanta of energy, what is its temperature for an external observer? It is 0. Absolute 0. This created an image of chilling perfection. The black hole was envisioned by scientists as an eternal, indestructible object. It could only grow. If you threw a star into it, the event horizon would expand. If you threw a book into it, it would get bigger. It never shrinks. It never gives energy back. In the 1960s, the great physicist John Archibald Wheeler, the same one who popularized the term black hole, formulated a principle that further simplified the picture. He famously said, "Black holes have no hair." It sounds amusing, but the meaning is profound. Hair in this context refers to complex details, nuances, or internal features. If you look at your friend, you see countless details: eye color, hairstyle, a mole on the cheek. A star has a chemical composition, surface spots, and magnetic storms. A planet has mountains and oceans. A black hole, according to the no-hair theorem, has none of this. A black hole is completely described by just 3 numbers. Only 3. First, mass, how much matter fell into it. Second, electric charge, though real holes are likely neutral as they quickly attract opposing charges. And third, angular momentum, or spin, how fast it rotates. That's it. No other parameters. It does not matter if the black hole was formed from gold, hydrogen, or the collected works of Shakespeare. Once the event horizon forms, all information about the matter's structure is erased from the external world. All that remains is the smooth, ideal geometry of space-time. It was a beautiful, finished canvas. Black holes were the icy titans of the universe. They were the ultimate sink for entropy, the cosmic wastebasket that never overflowed and never smelled. General relativity seemed to have provided the final exhaustive answer. But physicists are a restless bunch, especially when they see something too perfect to be true. Within this portrait of cold perfection lay a tiny flaw, a barely visible crack that threatened to bring down the entire edifice of theoretical physics. The problem revolved around the word entropy. I mentioned it briefly, but let us look deeper. Classical physics claimed a black hole is an object without internal structure, apart from the singularity. It is a simple object. And in thermodynamics, simplicity implies a lack of entropy. Entropy is a measure of disorder, a measure of the number of possible states a system can be in. Gas in a room has enormous entropy because the molecules can fly anywhere. A crystal at absolute zero has zero entropy because every atom is locked rigidly in place. If a black hole has no hair, if it is described by only 3 numbers, it is ordered to the maximum extent. Therefore, its entropy must be zero. And here, a monstrous contradiction arises. Imagine you have a container of hot gas. It has high entropy, a lot of chaos. We take this container and drop it into a black hole. What happens? For us, external observers, the container vanishes. Its entropy has disappeared from our observable universe, and the black hole, as we have established, has zero entropy. Thus, the total entropy of the universe has decreased. But this is impossible. The second law of thermodynamics is arguably the most unbreakable law of nature. It states, the entropy of a closed system can only increase or remain unchanged. Chaos always increases. A cup breaks, but it doesn't reassemble itself. Heat flows from hot to cold, never the reverse. You cannot simply take disorder and destroy it, wiping it from existence. If the classical black hole truly has zero temperature and zero entropy, it is a criminal. It violates the second law of thermodynamics every time it swallows something. It allows us to decrease the world's entropy simply by throwing trash over the event horizon. This was a dead end. Either the second law of thermodynamics was wrong, a belief held by almost no one, or our understanding of black holes was fundamentally flawed. In the early 1970s, a young graduate student at Princeton University named Jacob Bekenstein looked at this problem and proposed a solution that seemed like complete heresy. He suggested that the black hole does possess entropy, and that this entropy is enormous. But where is it stored if there is nothing inside? Bekenstein pointed to the surface, the event horizon itself. We will discuss this audacious hypothesis and how it led to the concept of a hot vacuum in the next part. For now, let us fix in our memory the image of that classical monster, a perfectly black sphere against the stars, colder than the deepest cosmos, silent, eternal, and flawlessly smooth. It was this image that Stephen Hawking would soon set out to destroy, even though his initial intention was to defend it. The world of classical physics was logical and rigorous, but it failed to account for what happens at the smallest scales, where the uncertainty of quantum physics holds sway. And when these two worlds, the world of immense gravity and the world of tiny particles, met, an idea was born that changed everything. We concluded that the classical black hole is an ideal, cold and eternal object. It is like an impeccable marble sphere resting on the black velvet of the cosmos. But in physics, as in life, perfect objects often cause the biggest problems. And the issue confronting scientists in the early 70s was not just a technical snag. It was a fundamental crisis threatening to undermine one of the pillars of our understanding of the universe: thermodynamics. Let us discuss entropy once more. The word is often used as a synonym for chaos or disorder. While true, that definition is too superficial for our purpose. To grasp the essence of the black hole paradox, we need to view entropy through the lens of the great Austrian physicist Ludwig Boltzmann in the 19th century. Imagine your desk. It has papers, pens, a coffee mug, and books. you neatly stack everything and align it perfectly, this is a state of order. It has low entropy. Why? Because there are very few ways to arrange things so that they look perfectly ordered. Shift a pen 2 centimeters left and the symmetry is broken. Now, imagine a mess. Papers scattered, pens lying randomly. This is a state of high entropy. Why? Because there are a million ways to scatter things so that the desk looks untidy. You can swap 2 crumpled pieces of paper and the overall impression of disorder remains the same. Boltzmann realized that entropy is, in reality, a measure of hidden information. It is the number of microscopic states that look identical to an external observer. The more options for a system's internal arrangement result in the same external picture, the higher the entropy. And here, the second law of thermodynamics steps in. It is arguably the most depressing, but also the most majestic law of nature. It states, in any closed system, entropy cannot decrease. It either remains constant or increases. The universe tends from order to chaos, from uniqueness to average uniformity. This is the famous arrow of time. Why do we remember the past but not know the future? Because entropy was lower in the past. If you drop a cup from a table, it shatters into hundreds of fragments. Entropy sharply increases. But you will never see the shards spontaneously leap from the floor, re-glue themselves in mid-air, and gently land on the table as a whole cup. Newton's laws of mechanics allow this motion. If you run the film backward, no law of motion is violated. But the second law of thermodynamics imposes a strict veto on it. The probability of such an event is so remote, it can be considered zero. So, entropy always increases. This is an ironclad rule. If you burn a book, the information does not vanish without a trace. It turns into heat, into the chaotic motion of molecules, smoke, and ash. The book's entropy is transferred to the environment's entropy and has increased. Now, let's return to John Archibald Wheeler, the legendary American theoretical physicist. Wheeler enjoyed posing provocative questions that stumped his colleagues and students. Once, he proposed a thought experiment that sounded deceptively simple. Imagine, he said, I pour myself a cup of hot tea. The cup of tea has entropy. It is quite high. Water and tea molecules move chaotically, colliding. Steam rises. This cup contains information about its temperature, chemical composition, and the motion of every single particle. Now, he continued, imagine I take this cup and throw it into a black hole. Let's follow the process. The cup crosses the event horizon. For us, the external observers, it has disappeared. It is no longer part of our observable universe. Along with it, all its entropy has vanished. But wait, we just said the classical black hole is an object with zero entropy. It has no hair. It is perfectly smooth and simple. The arithmetic is this. We had a universe with entropy S. We took a portion of that entropy, the cup of tea, and discarded it into a trash can that by itself has no entropy. As a result, the universe's total entropy has decreased. We have just violated the second law of thermodynamics. We have committed a crime against the fundamental structure of reality. If this were possible, all of our physics would collapse. If entropy can be destroyed, perpetual motion machines are possible. Causality could be violated, and chaos could be reversed without expending energy. This was a disaster. It implied that black holes were magical vacuum cleaners that could sanitize the universe of entropy. One only needed to dump all their waste, all the exhausted gas, all the heat into them, and the universe would become progressively more ordered, contrary to the second law. Wheeler understood that nature could not permit such cheating. There had to be an error in our reasoning. Either the second law of thermodynamics was wrong, a belief held by almost no one, or our understanding of black holes was fundamentally flawed. In the early 1970s, a young graduate student at Princeton University named Jacob Bekenstein looked at this problem and proposed a solution that seemed like complete heresy. He suggested that the black hole does possess entropy, and that this entropy is enormous. But where is it stored if there is nothing inside? Bekenstein pointed to the surface, the event horizon itself. We will discuss this audacious hypothesis and how it led to the concept of a hot vacuum in the next part. For now, let us fix in our memory the image of that classical monster, a perfectly black sphere against the stars, colder than the deepest cosmos, silent, eternal, and flawlessly smooth. It was this image that Stephen Hawking would soon set out to destroy, even though his initial intention was to defend it. The world of classical physics was logical and rigorous, but it failed to account for what happens at the smallest scales, where the uncertainty of quantum physics holds sway. And when these two worlds, the world of immense gravity and the world of tiny particles, met, an idea was born that changed everything. We concluded that the classical black hole is an ideal, cold and eternal object. It is like an impeccable marble sphere resting on the black velvet of the cosmos. But in physics, as in life, perfect objects often cause the biggest problems. And the issue confronting scientists in the early 70s was not just a technical snag. It was a fundamental crisis threatening to undermine one of the pillars of our understanding of the universe, thermodynamics. Let us discuss entropy once more. The word is often used as a synonym for chaos or disorder. While true, that definition is too superficial for our purpose. To grasp the essence of the black hole paradox, we need to view entropy through the lens of the great Austrian physicist Ludwig Boltzmann in the 19th century. Imagine your desk. It has papers, pens, a coffee mug, and books. If you neatly stack everything and align it perfectly, this is a state of order. It has low entropy. Why? Because there are very few ways to arrange things so that they look perfectly ordered. Shift a pen 2 centimeters left and the symmetry is broken. Now, imagine a mess. Papers scattered, pens lying randomly. This is a state of high entropy. Why? Because there are a million ways to scatter things so that the desk looks untidy. You can swap 2 crumpled pieces of paper, and the overall impression of disorder remains the same. Boltzmann realized that entropy is, in reality, a measure of hidden information. It is the number of microscopic states that look identical to an external observer. The more options for a system's internal arrangement result in the same external picture, the higher the entropy. And here, the second law of thermodynamics steps in. It is arguably the most depressing, but also the most majestic law of nature. It states, in any closed system, entropy cannot decrease. It either remains constant or increases. The universe tends from order to chaos, from uniqueness to average uniformity. This is the famous arrow of time. Why do we remember the past but not know the future? Because entropy was lower in the past. If you drop a cup from a table, it shatters into hundreds of fragments. Entropy sharply increases. But you will never see the shards spontaneously leap from the floor, re-glue themselves in mid-air, and gently land on the table as a whole cup. Newton's laws of mechanics allow this motion. If you run the film backward, no law of motion is violated. But the second law of thermodynamics imposes a strict veto on it. The probability of such an event is so remote it can be considered zero. So, entropy always increases. This is an ironclad rule. If you burn a book, the information does not vanish without a trace. It turns into heat, into the chaotic motion of molecules, smoke, and ash. The book's entropy is transferred to the environment's entropy and has increased. Now, let's return to John Archibald Wheeler, the legendary American theoretical physicist. Wheeler enjoyed posing provocative questions that stumped his colleagues and students. Once, he proposed a thought experiment that sounded deceptively simple. "Imagine," he said, "I pour myself a cup of hot tea. The cup of tea has entropy. It is quite high. Water and tea molecules move chaotically, colliding. Steam rises. This cup contains information about its temperature, chemical composition, and the motion of every single particle. Now," he continued, "imagine I take this cup and throw it into a black hole. Let's follow the process. The cup crosses the event horizon. For us, the external observers, it has disappeared. It is no longer part of our observable universe. Along with it, all its entropy has vanished. But wait, we just said the classical black hole is an object with zero entropy. It has no hair. It is perfectly smooth and simple. The arithmetic is this. We had a universe with entropy S. We took a portion of that entropy, the cup of tea, and discarded it into a trash can that, by itself, has no entropy. As a result, the universe's total entropy has decreased. We have just violated the second law of thermodynamics. We have committed a crime against the fundamental structure of reality. If this were possible, all of our physics would collapse. If entropy can be destroyed, perpetual motion machines are possible. Causality could be violated, and chaos could be reversed without expending energy. This was a disaster. It implied that black holes were magical vacuum cleaners that could sanitize the universe of entropy. One only needed to dump all their waste, all the exhausted gas, all the heat into them, and the universe would become progressively more ordered, contrary to the second law. Wheeler understood that nature could not permit such cheating. There had to be an error in our reasoning. Either the second law of thermodynamics was not universal and did not apply in the presence of gravity, which would be strange and deeply troubling for physicists, or we were wrong about black holes. What if the black hole doesn't have zero entropy? What if, upon swallowing the cup of tea, the black hole somehow changes? But how can it change? We remember the theorem. Black holes have no hair. Mass, charge, spin. Nothing more. If we toss a cup of tea into the hole's mass will slightly increase. Charge and spin might also change. But is that enough to conceal the enormous entropy that was in the cup? It seemed like an impasse. On one side, the flawless mathematics of general relativity insisted that the black hole was simple geometry. On the other, the unshakable laws of thermodynamics demanded that entropy never vanish. Two great branches of physics collided head-on. And, as often happens in science, the solution came not from a seasoned professor, but from a young student who hadn't yet learned that such thinking was forbidden. Wheeler was discussing this problem with his graduate student at Princeton University. The young man was named Jacob Bekenstein. It was Bekenstein who made the intellectual leap that initially seemed like utter nonsense to everyone, including Stephen Hawking. Bekenstein looked at the black hole and asked, "What exactly grows when we throw something into it?" "The mass grows. And if the mass grows, the radius of the event horizon also grows. And if the radius grows, the surface area of the horizon increases." Wait, Bekenstein thought. The area of a black hole's event horizon never decreases. This had been mathematically proven by Stephen Hawking. You can throw matter into it, the area increases. You can collide two black holes. The area of the resulting hole will be larger than the sum of the original two. You cannot do anything to decrease this area, at least in classical physics. This sounds very much like entropy, Bekenstein concluded. Entropy never decreases either. Could the area of the event horizon be the entropy? At first glance, it sounded like a beautiful but empty analogy. So what if both quantities grow? My age is also always increasing, and the pile of garbage at the landfill grows. That does not mean my age is entropy. But Bekenstein persisted. He suggested that this was no mere analogy. He declared that a black hole possesses real physical entropy, and this entropy is directly proportional to the area of its event horizon. This statement was revolutionary. It rescued the second law of thermodynamics. Now, when you toss a cup of tea into a black hole, the cup's entropy does not vanish. It is converted into an increase in the horizon's area. The universe pays for the cup's disappearance by the black hole becoming slightly larger. The balance holds. The thermodynamic crime is prevented. However, in solving one problem, Bekenstein immediately created another, even more terrifying one. And it is this conflict, which became known as the Bekenstein heresy, that we must discuss next. Because if a black hole has entropy, it must possess one more characteristic whose existence was denied by every physicist in the world. So, imagine the atmosphere at Princeton in the early 70s. The young graduate student, Jacob Bekenstein, comes to his advisor, Dr. Wheeler, and essentially declares, "I know how to save thermodynamics. The black hole isn't just a bottomless pit. It has a surface covered in bits of information." Bekenstein's idea was beautiful in its geometric simplicity. Let's try to visualize it. Imagine the black hole's event horizon as a sphere, a giant black soap bubble. Bekenstein proposed mentally dividing the surface of this bubble into tiny squares. How tiny? The smallest possible in nature, the Planck length. This is 10 to the negative 35th meters. It is so small that if an atom were enlarged to the size of the visible universe, the Planck length would be the size of a tree. Bekenstein hypothesized that each of these tiny squares on the horizon's surface holds one bit of information, a 1 or a 0, yes or no. This was a striking insight. It meant that the informational capacity of a black hole, how much you can stuff into it, does not depend on its volume, as we are accustomed to thinking about suitcases or rooms, but on its surface area. Imagine you want to know how many books can fit in a library. Normally, you measure the volume of the hall. But in the case of a black hole, Bekenstein was saying, "No, don't look inside. Look at the walls." The number of books that can be hidden inside depends only on the area of the walls. If entropy is proportional to the area, the second law of thermodynamics is saved. When the cup of tea falls in, it disappears, but the horizon's area increases just enough to compensate for the cup's lost entropy. The universe's balance is restored. It seemed perfect. Wheeler was intrigued, but the scientific community greeted the idea with immense skepticism. And the loudest critic was, ironically, Stephen Hawking. At the time, Hawking was already a rising star in cosmology, confined to a wheelchair, but with a mind sharper than most healthy people. It was Hawking who had previously proven the theorem that the event horizon's area cannot decrease in classical processes. But when he heard Bekenstein's interpretation of his theorem, he was, to put it mildly, not pleased. Hawking later recalled that it even irritated him. He felt Bekenstein was abusing his discovery, forcing a superficial analogy. Why was Hawking so categorical? What was the problem? The issue is that thermodynamics is a very strict science. All its quantities are linked by indissoluble chains of equations. You cannot simply say, "This object has entropy," and walk away for coffee. If an object has entropy, it automatically and inevitably entails consequences. The main consequence is this. If a body has entropy and energy, and a black hole's mass is energy, according to E equals mc squared, then this body must have a temperature. That is the law. Entropy and temperature are like Siamese twins. You cannot have one without the other. And if a body has a temperature above absolute zero, it is obligated to emit heat. It must glow. This is where Bekenstein's logical chain crashed into the wall of classical physics. A black hole has entropy, per Bekenstein. Therefore, a black hole has temperature. Therefore, a black hole must radiate. But a black hole, by definition, is an object that cannot emit anything. The event horizon is a one-way street. Nothing leaves a black hole. Hawking reasoned. Bekenstein's idea is contradictory. If we accept it, we must concede that black holes glow, but we know this is impossible. Therefore, the premise is false. Black holes have no entropy, and the coincidence in the behavior of area and entropy is merely an amusing mathematical curiosity, a coincidence with no physical meaning. The critique was devastating. Bekenstein seemed cornered. His theory demanded the impossible. A black hole with a temperature is an oxymoron, physicists argued. It's like dry water or hot ice. If it has a temperature, it must surrender energy. If it surrenders energy, something must fly out of it, and nothing can fly out of it. Bekenstein defended himself as best he could. He argued, "I am not claiming it radiates. I am merely saying that thermodynamics demands the existence of entropy. Perhaps it has a temperature, but for some reason does not radiate." But this was a weak justification. Physics does not tolerate such exceptions. The situation reached a breaking point. This was a classic scientific conflict. A beautiful hypothesis collided with an ironclad fact. The fact was that general relativity strictly forbade radiation. The hypothesis was that thermodynamics required entropy. Someone had to yield, either Einstein or Boltzmann. Hawking decided to settle the dispute. He resolved to mathematically prove Bekenstein wrong. His plan was to perform precise, rigorous calculations of what happens to quantum fields near a black hole and show that there was no radiation. Entropy was zero, and Bekenstein was merely toying with analogies. But to do this, he needed to dive deeper into quantum mechanics. Until that moment, black holes had been studied only as objects of gravity. No one had seriously tried to apply the equations of the quantum world to them. The irony of fate was that the very desire to disprove Bekenstein led Hawking to the greatest discovery of his life. But before that happened, a crucial event took place. An event often overlooked in Western history textbooks, but one that played a key role. Hawking traveled to Moscow. It was 1973, the height of the Cold War. But science, thankfully, finds ways to penetrate even the most formidable barriers. In Moscow, the strongest school of theoretical physicists was working, led by the legendary Yakov Zeldovich. Hawking knew that the Russians had stumbled upon something important. He knew they were also working on the black hole problem, and he decided to discuss his doubts with them. What transpired in Moscow became the turning point. It was a meeting where Hawking's classical certainty showed its first crack. We will talk about this historic visit, the late-night debates at the hotel, and the ingenious intuition of the Soviet scientists, because it was there, in the Soviet Union, that the thought was first voiced. What if a black hole can glow, but not quite in the way we imagine? September 1973. Moscow is beginning to embrace the autumn chill. Stephen Hawking arrives in the Soviet capital. By this time, he was already using a wheelchair, but he could still speak independently, though his speech was becoming increasingly slurred, comprehensible only to those close to him and his colleagues. He was accompanied by his wife Jane and his friend and fellow physicist Kip Thorne. The purpose of the visit was to meet with Yakov Zeldovich. Zeldovich was a legend. A joke even circulated in the West. Zeldovich is not one man, but the name of an entire secret institute, due to the incredibly broad scope of his interests, which spanned everything from combustion and nuclear weapons to cosmology and elementary particles. But Zeldovich was a very real, energetic man with sparkling eyes and an extraordinary intuition. Working alongside Zeldovich was his brilliant young student, Alexei Starobinsky. The meeting took place, according to some accounts, at a local conference center, or perhaps at the physics department of the Lebedev Institute. What mattered were not the walls, but the conversation within them. The discussion focused on rotating black holes. In physics, rotating black holes are called Kerr black holes, named after the New Zealand mathematician Roy Kerr, who found their description. They are far more interesting and complex than the simple, non-moving Schwarzschild black holes. A rotating black hole has an additional zone around the event horizon, the ergosphere. This is a region where space-time rotates so rapidly that it drags all matter along with it. It is impossible to remain stationary relative to distant stars there, just as it is impossible to stand still in a raging whirlpool. Zeldovich and Starobinsky proposed that Hawking consider an astonishing effect known as superradiance. Imagine a spinning metal cylinder. If you direct an electromagnetic wave, light, or a radio wave at it from the correct angle, the reflected wave can become stronger than the incident wave. It steals a bit of rotational energy from the cylinder and flies away, amplified. The physicists asserted the same must happen with a spinning black hole. If a wave is sent toward it, it can reflect with greater energy by slowing the hole's rotation. This was a classical effect requiring no quantum mechanics. But then, Zeldovich made his famous intuitive leap. He said, essentially, Stephen, if a spinning hole can amplify incoming waves, then, according to quantum mechanics, it must spontaneously generate those waves itself, even if nothing is falling onto it. The logic was based on the principle of spontaneous emission. In the quantum world, anything that can be amplified, stimulated emission, can also happen by itself, spontaneous emission. The vacuum is not empty. Fluctuations, tiny bursts of energy, are constantly being born within it. Zeldovich and Starobinsky convinced Hawking a rotating black hole must interact with the vacuum and generate particles. It must glow by consuming its own rotational energy until it spins down. For Hawking, this was a revelation. He had come to Moscow skeptical of the idea of radiation. He was still focused on his battle with Bekenstein, determined to prove that black holes were dead and cold. And here were two brilliant physicists showing him that rotating holes were obligated to radiate. Hawking debated. He pointed out possible flaws in their reasoning. But in the end, returning to his hotel room, he realized their arguments had ironclad logic. The uncertainty principle, combined with the rotation of the horizon, truly must generate particles. However, Zeldovich and Starobinsky only spoke of rotating holes. They believed that once the hole stopped spinning, the radiation would cease. A standard, non-rotating black hole would remain cold and eternal. This seemed like a reasonable compromise. Rotation is an active process, kinetic energy that can be harvested. Mass is just mass. Hawking returned to Cambridge energized. He had a goal. He wanted to mathematically derive, with rigorous precision, what Zeldovich and Starobinsky had predicted intuitively. He aimed to find the exact formula for the radiation of a rotating black hole. He set to work. It was months of intense labor. Hawking used the complex machinery of quantum field theory in curved space-time. He constructed equations describing the behavior of wave packets near the horizon. He expected to obtain the following result. A rotating hole radiates, as the Russians said. A non-rotating hole is silent. The radiation equals zero. But when, by early 1974, he finally brought all the equations together, he saw something that sent a chill down his spine. The math was telling him that he was wrong. The result for the non-rotating hole was not zero. Hawking checked again. An error? No. Again. Perhaps a minus sign was lost somewhere. No. The equations stubbornly insisted, even if the black hole is not spinning, even if it is perfectly motionless, it still radiates. It glows. And the spectrum of this glow corresponded exactly to the spectrum of thermal radiation, a spectrum predicted by temperature. The temperature was dependent on the entropy Jacob Bekenstein had talked about. In that moment, Hawking must have experienced a feeling rarely granted to a human being, a mixture of terror and ecstasy. Terror because the familiar worldview was crumbling. Ecstasy because a truth no one had ever seen before was laid bare before him. Bekenstein had been right. All that time, while Hawking argued against him, while he tried to disprove him, the equations whispered, Bekenstein is correct. But Bekenstein had been right only intuitively. He had guessed the answer without knowing the solution. And Hawking now held the mechanism in his hands. What was the essence of this discovery? It turned out that the very concept of a particle in the universe is not absolute. We are used to thinking that an electron is an electron, no matter where it is, be it on Earth or on Mars. But Hawking showed that in curved space-time, this is not true. What one observer, falling into the hole, considers to be an empty vacuum, another observer, suspended far from the hole, sees as a stream of hot particles. The black hole's gravity so powerfully distorts the notion of time and space that the very definition of a vacuum breaks down. The vacuum ceases to be empty. Hawking derived the formula for a black hole's temperature. Today, this formula is carved into his memorial stone at Westminster Abbey. It is astonishingly concise, yet it unites all the key constants of physics. It contains Boltzmann's constant, the herald of thermodynamics and heat; Planck's constant, the symbol of quantum mechanics; the speed of light, the foundation of relativity; and Newton's gravitational constant, the basis of gravity. All four fundamental pillars of nature met in a single line. This was a triumph. It was the holy grail of theoretical physics. For the first time, gravity and quantum mechanics were linked, not through words, but in a strict mathematical equality. But what did this mean for reality? It meant that black holes are not eternal. If they emit heat, they lose energy. And energy, as we know from Einstein, is equivalent to mass. By radiating, a black hole loses mass. It shrinks. It evaporates. Imagine the implications of this conclusion. Before, we thought a black hole was the end of the story. Everything that fell in stayed there forever. The hole could only grow. It would exist forever, even after all the stars burned out. Now it was revealed that black holes are mortal. They slowly, very slowly, but inexorably, melt away like an ice cube in the sun. They return energy to the universe. Hawking published his work in the journal Nature in 1974. The article was modestly titled Black Hole Explosions. The title ended with a question mark, but the content left no room for doubt. The scientific world was in shock. The initial reaction of most physicists was the same as Hawking's own had been at the start. This cannot be. At a conference in Oxford, where Hawking first presented his results, the session chairman, John Taylor, leapt up and declared, "I'm sorry, Stephen, but this is utter rubbish. It simply cannot be." Why such a drastic reaction? Because it demolished the concept of the event horizon as an absolute barrier. If the hole radiates, then something is escaping. But how, if the speed of light cannot be overcome? Hawking needed to explain the physical meaning of his equations. Mathematics is fine, but people, even very smart scientists, need images. They need the mechanism of the process. How exactly does a particle leave the prison from which there is no exit? Hawking then proposed the famous analogy with virtual particles. This explanation, which has since travelled from textbook to textbook, is slightly simplified, and some physics purists criticize it, but it is the best way to understand the core idea. Let us try to imagine the vacuum. Not the technical vacuum created by pumps in a laboratory, but the true cosmic vacuum. Classical physics told us the vacuum is emptiness, nothing, zero, silence. Quantum physics tells us the vacuum is a lie. In reality, the space around you, the space between stars, even the space inside your atoms, is a seething soup. It is an arena of frenzied activity. According to Heisenberg's uncertainty principle, nature hates exact zeros. The energy of a field can never be strictly zero. It always fluctuates, trembles. In this quantum soup, miracles constantly happen. Pairs of particles are born from nothing, a particle and its antiparticle, an electron and positron, for instance, or two photons. They appear for an instant, borrowing energy from the vacuum. They fly apart, complete a tiny loop, and then collapse back together, annihilating and returning the energy. This happens everywhere, constantly, billions of times per second in every cubic centimeter of space. We call these particles virtual because they live too briefly for us to directly detect them. They are like ghosts, appearing and disappearing without a trace. It's a quantum credit, borrowed energy, returned energy. The balance is met. But what happens if this dance occurs on the edge of a precipice, at the event horizon of a black hole? Imagine a pair of virtual particles born right on the boundary. One particle appears just outside, and the other appears just inside. Normally, they would attract each other and vanish. But here, monstrous gravity intervenes. The particle that appeared inside the horizon is instantly imprisoned. There is no way back for it. It falls toward the singularity. Its partner, left outside, is suddenly alone. It has no one to annihilate with. Its partner has vanished behind the wall. The remaining particle cannot simply disappear. It becomes real. It transforms from a virtual ghost into a genuine material object, a photon, an electron, or a neutrino. And if it has enough velocity, it flies away from the black hole. To a distant observer, to you and me, this looks as if the black hole has just spat out a particle. But here arises the most difficult question, one that trips up many trying to understand this theory. Wait, you might say, the particle flew away. That is energy. Energy cannot come from nowhere. Therefore, someone must have paid for it. Who pays the bill? The black hole. But how? After all, the second particle fell into the black hole. The hole swallowed one particle and emitted another. It seems the hole's mass should increase. It ate something, and the universe's energy should also increase. A new particle appeared. Is the law of conservation of energy violated? No. And here lies the most subtle point. In the world of physics, energy is relative. Near a black hole, the gravitational field is so powerful that it changes signs. For the virtual pair to become real, energy is needed, a lot of it. Where does it come from? It is drawn from the hole's gravitational field. The particle that flies outward carries away positive energy. It becomes a real part of our world. But the law of conservation is relentless. If you create a plus, you must create a minus. The sum must remain zero or unchanged. Consequently, the particle that falls inward to compensate for the birth of its partner must carry negative energy. This sounds strange to our everyday experience. We are accustomed to energy always being positive. Mass is positive. But in quantum field theory, in a strong gravitational field, a state of negative energy relative to an observer at infinity exists. The falling particle is a kind of anti-energy. It is a debt. When it crosses the horizon and falls to the center, it adds negative energy to the black hole. What happens when you add a negative number to a number? It decreases. If you have $100 and add a $5 debt, you have $95 left. The black hole is the same. By absorbing a negative energy particle, it reduces its mass by exactly the amount the escaping particle carried away. Therefore, when we look at the black hole from afar, we see a perfect balance. The hole loses mass, and the surrounding space is filled with radiation. The hole is literally converting its own mass into light and heat, using the vacuum as an intermediary. This process is incredibly beautiful. The black hole does not just sit in the dark. It is surrounded by a halo of faint glow, woven from particles that manage to escape the fate of their fallen partners. But here is the crucial caveat. This process is very, very weak for large black holes. the gravity at the horizon of a giant hole is not that steep. The tidal forces there, the difference in gravity over small distances, are weak, so it is hard to tear the virtual pair apart. For a black hole with the mass of the Sun, the temperature of this radiation is only about 60 billionths of a Kelvin. This is practically zero. It is impossible to detect such radiation with any modern instrument. But the smaller the black hole, the steeper its horizon, the sharper the gravitational gradient, and the easier it is to rip pairs apart. This brings us to the most paradoxical property of Hawking radiation. In the normal world, if you heat something, it cools down by radiating heat. A cup of tea cools, an iron cools, a star cools. With black holes, it is the opposite. They behave like furious thermodynamic monsters. The more energy they lose, the hotter they become. The more they evaporate, the brighter they glow. This is called negative heat capacity. And it is this property that transforms the slow, majestic evaporation into a catastrophic explosion capable of outshining galaxies in the final moments of a black hole's life. Imagine you put a kettle on the stove. You turn on the gas, supply energy, the water temperature rises, and the water boils away. But the boiling temperature remains the same, 100 degrees Celsius. Now, imagine an anti-kettle. The less water it holds, the higher the temperature. When there is a lot of water, it is icy. When only a film is left at the bottom, it is scorching hot at 1000 degrees. When only a single drop remains, a nuclear explosion occurs. It sounds like madness. Welcome to the thermodynamics of black holes. The formula Stephen Hawking derived contains an astonishing dependency. The black hole's temperature is inversely proportional to its mass. Let's write that in words. T equals constant divided by m. If the mass m is large, the denominator is large, and the temperature T is small. If the mass is small, the denominator is small, and the temperature is enormous. Let us look at specific examples to grasp the scale. Take a typical astrophysical black hole, one resulting from the death of a massive star. Suppose its mass is 10 times that of our Sun. According to Hawking's formula, its temperature would be only about 6 nanokelvin. That's 6 billionths of a degree above absolute zero. This is incredibly cold. For comparison, the temperature of deep space today is about 2.7 Kelvin. This is the temperature of the cosmic microwave background, CMB, the echo of the Big Bang that permeates the entire universe. What does this mean? It means the cosmos is hotter than the black hole. If you put a piece of ice in an oven, it will melt, absorbing heat. A black hole is currently in that exact position. It lies in the warm bath of the CMB radiation. Photons from space fall into it, heat it, and add mass. As long as the universe's temperature is above the hole's temperature, the black hole does not evaporate. It grows. It absorbs more energy from the vacuum than it gives off via Hawking radiation. That is why, right now, in our epoch, all stellar mass black holes are silent. They are only gaining weight. They are predators in an active feeding phase. What about supermassive black holes? Those giants at the centers of galaxies with masses in the billions of suns? They are even colder. Their temperature is so close to absolute zero that distinguishing it from zero is nearly impossible. They will continue to grow for trillions of years. But the universe changes. It expands. As it expands, the CMB cools. A moment will come, a very, very long time from now, billions of years in the far future, when the cosmos's temperature drops below the black hole's temperature. And then, the most interesting part will begin. The process will reverse. The black hole will start giving more than it receives. It will begin to shrink. And now, remember our paradox. The black hole loses mass, so it becomes lighter. According to the formula, if the mass decreases, the temperature rises. The black hole heats up. And what does a heated body do? It radiates energy more intensely. Thermodynamics has the Stefan Boltzmann law. The power of radiation increases proportional to the fourth power of the temperature. If you double the temperature of a body, it begins to glow 16 times brighter. This creates a positive feedback loop. The process accelerates like an avalanche. The hole radiates, loses mass, heats up, radiates even more intensely, loses mass even faster, and heats up even more. It is a death spiral. Let's look at the other end of the spectrum. What if we could shrink a black hole down to the size of an atom? Such a hole would have the mass of, say, a small mountain or an asteroid. Its temperature would no longer be nanokelvin, but billions of degrees. Such a hole would glow not with darkness, but with blinding X-ray and gamma radiation. It would look like a tiny yet incredibly fierce white star. If such a primordial black hole flew through the solar system, we would certainly notice it. It would not absorb light. It would function as a powerful searchlight. This property, negative heat capacity, makes black holes unique objects. In ordinary life, systems strive for equilibrium. If you put a hot mug on a table, it cools to room temperature, and the process stops. A black hole never achieves equilibrium with its environment. It either absorbs everything and freezes, or it begins to radiate and heats up endlessly until it vanishes. It is inherently unstable. How long does it take for an ordinary black hole to evaporate completely? The numbers here defy human imagination. For a black hole with the mass of the Sun, it would take approximately 10 to the 67th power years. That is a 1 followed by 67 zeros. The age of our universe is currently only 13.8 billion years, 10 to the 10th years. Black holes live almost forever. Compared to them, stars, galaxies, and civilizations are instantaneous flashes. But almost is not forever. Sooner or later, that term will expire. And here we approach another mystery. What happens when the acceleration process reaches its limit? Imagine a black hole has been evaporating for trillions upon trillions of years. It is small now. It is the size of a proton. Its temperature has reached Planck scales, the highest temperatures possible in physics. At this moment, the evaporation turns into a detonation. In the final second of its life, the black hole releases energy equivalent to the blast of millions of hydrogen bombs. This is the final chord, the farewell scream of the gravitational monster. After that, is there emptiness or something else? Here, physics reaches another impasse. Hawking's formulas work perfectly as long as the hole is large. But when it becomes microscopic, when its size is comparable to the wavelength of the emitted particles, our theory breaks down. We do not know exactly what happens in the very last moment. Does it disappear entirely, leaving no trace? Or does a cinder remain, a microscopic residue, a plankton, a kind of diamond of memory that cannot be destroyed? This question is directly linked to the problem that has plagued scientists for half a century. If the black hole disappears, where does everything that fell into it go? Where does the information go? It is the information paradox we will discuss next. Because Hawking radiation, while solving one problem with entropy, created another problem that questions our very ability to predict the future and remember the past. But before we move to the philosophy of information, we need to understand one more strange thing. Why does an observer falling into the hole see no radiation, yet we, sitting safely, see the hole burning? The answer was provided by Hawking's colleague, William Unruh, and his discovery showed that even the concept of temperature in the universe is merely an illusion of perception. We have established that black holes radiate. They are hot. But here is a nuance that can drive anyone trying to think in conventional terms mad. Imagine you are a brave astronaut. You decide to sacrifice yourself for science and jump into a black hole. You put on your suit, turn on your cameras, and fall. You freefall toward the event horizon. What will you see at the moment you cross the line? Will you see the blinding flash of Hawking radiation? Will you feel the heat we discussed in previous sections? Will you be burned alive? The answer general relativity gives us is astonishing. No, you will see nothing special. For you, the freely falling observer, the event horizon is a phantom. You will fly right through it without feeling any heat. Your thermometer will read absolute zero, discounting the cosmic background radiation. But wait, how can this be? We just spent several chapters proving that for an external observer who hangs at a safe distance, the hole is hot. It glows. It evaporates. A paradox arises. Two observers look at the same place in space. One says, "It's empty and cold here, a vacuum." The other says, "Are you insane? It's scorching hot here. There are masses of particles." Who is right? It turns out both are right. To understand this, we must familiarize ourselves with the effect discovered by the Canadian physicist William Unruh in 1976. The Unruh effect is perhaps the strangest consequence of quantum field theory. It states, "The very concept of a particle is not an objective fact of reality. The existence of particles depends on how you are moving." Let's conduct a thought experiment. Imagine you are in deep space, in a perfect vacuum. There is nothing around, not a single star, not a single atom. The temperature is absolute zero. Your Geiger counter is silent. Now imagine you turn on your rocket engines, but you do not just fly at a constant speed. You start accelerating. You press the gas harder and harder. Your acceleration becomes monstrous. What happens? According to Unruh's calculations, as your acceleration increases, your Geiger counter will suddenly begin to click. It will start registering particles. You will feel warmth. The vacuum, which was just cold and empty for you, the accelerating observer, will turn into a warm bath of photons and other particles. Where did they come from? Did you heat the vacuum by friction? No, there's nothing to rub against in a vacuum. It's all about horizons. When you move with acceleration, a zone forms behind you from which light can never catch up to you. You are running away from the light too fast. This creates an artificial event horizon, similar to a black hole's horizon. The quantum fluctuations of the vacuum, those virtual pairs we discussed, begin to behave differently in the presence of this horizon. For the accelerated observer, virtual particles become real. The energy for their materialization is provided by your engine, your force of acceleration. The Unruh temperature formula is very similar to Hawking's formula. Temperature is directly proportional to your acceleration. To heat the vacuum to 1 Kelvin, just 1 degree above absolute zero, you would need to accelerate at about 10 to the 20 meters per second squared. That is an unimaginable acceleration that would instantly flatten a person into a pancake 1 atom thick. That is why we do not notice this effect in everyday life. When you run for a bus, you also heat the vacuum around you, but to such an infinitesimal degree that no instrument in the world could record it. But back to black holes. What is the connection here? Recall Einstein's equivalence principle. It stated that gravity and acceleration are the same thing. Standing motionless on the surface of the Earth is the same as flying in a rocket accelerating at 9.8 meters per second squared. The floor pushes up on your feet, preventing you from moving by inertia. Now, imagine you are hovering motionless right above the event horizon of a black hole. To avoid falling in, you need to turn your engines to full power. Gravity there is monstrous, so you need immense, incredible acceleration just to stay put. You are an accelerated observer, and according to the Unruh effect, the vacuum around you should boil. You will see a sea of hot particles. This is precisely what we call Hawking radiation. For the external observer who holds themselves back from falling, the hole is hot. Now, imagine the unfortunate person who is falling in. They do not turn on their engines. They are in a state of free fall, weightlessness. According to Einstein, free fall is equivalent to inertial motion, motion without acceleration. They have no acceleration, so there is no Unruh effect for them. Therefore, for them, the vacuum remains cold and empty. This is mind-blowing, isn't it? The same reality looks diametrically opposite. There are particles, cries the one suspended above the abyss. There are no particles, answers the one falling into it. And both are right. Particles are not tiny solid balls that either exist or do not. Particles are excitations of quantum fields. And how these excitations are registered depends on the state of your detector, that is, on your motion. This effect saves us from many logical contradictions, but it also brings us to the deepest problem in modern physics. If observers see different realities, what happens to information? If I see a book burning up in the hot glow of Hawking radiation, and my friend sees the same book, whole and undamaged, falling into the cold darkness, where does the true information about the book reside? For a long time, physicists thought this was not a problem. Well, it fell in, it burned up. Who cares? But when Stephen Hawking declared that black holes eventually evaporate completely, vanishing without a trace, the question ceased to be trivial. It became a war. Let's imagine you committed a crime. Not an ordinary one, but a perfect one. You stole secret documents that could change the course of history and want to destroy them so that no one can ever recover them. You could burn them, but from a physics perspective, that is unreliable. If we had a supercomputer and collected every molecule of smoke, every particle of ash, and every photon of light from the flame, we could theoretically run the equations of motion backward and restore the document's text. In the classical world, information is indestructible. This is called determinism. The past uniquely determines the future, and the future determines the past. In the quantum world, this rule is even stricter. It is called unitarity. The quantum wave function describing a system never loses information. It might become entangled, smeared out, or unreadable to us. But in the very structure of the universe, the data is preserved forever. This is the law of conservation of information. And then, in 1976, Stephen Hawking published a paper that claimed black holes violate this law. Hawking's logic was devastatingly simple. The black hole evaporates by emitting Hawking radiation. This radiation is thermal. This means it is completely random and chaotic. It does not depend on what fell into the hole. Whether you threw in a volume of Shakespeare or a piece of rotten meat, the outgoing radiation will be identical. It depends only on the hole's mass, charge, and spin. When the black hole fully evaporates, only this chaotic thermal radiation remains. Question: where did the information about the volume of Shakespeare go? In the ash of the burned book, it is present in the complex structure of the molecules. In Hawking radiation, it is not, because it is born at the horizon from the vacuum and does not know what is inside. Hawking's conclusion: information has vanished. It is erased from existence. The black hole is a cosmic shredder that destroys not only matter, but the memory of it. When Hawking presented this idea at a conference in Chicago, the American physicist Leonard Susskind and the Dutch genius Gerard 't Hooft were in the room. They were horrified. Susskind later recalled that he could not believe his ears. If Hawking was right, all of quantum mechanics was flawed. Why is this so terrifying? It seems like, well, a few bits of information disappeared. So, what? The problem is that everything in physics is interconnected. If you allow a violation of unitarity, the loss of information, in even one place, the black hole, then mathematically it infects the entire theory. This leads to energy no longer being conserved everywhere. The probabilities of events cease to add up to 100%. The world becomes unpredictable and absurd at a fundamental level. The temperature in your room could suddenly spike to 1,000,000 degrees for no reason. Susskind and 't Hooft realized a war had begun. Either Hawking was wrong, or the physics we had been building for 100 years had to be discarded. The dispute lasted for decades. It became known as the Battle of the Black Hole. In 1997, the famous bet was struck. On one side, Stephen Hawking and Kip Thorne, who bet that information is lost. On the other side, John Preskill and, tacitly, Susskind, who bet that information is preserved. The stake was an encyclopedia. The winner would receive an encyclopedia of their choice, from which information could be retrieved at will. Hawking's position was strong because of its reliance on general relativity. Gravity is so strong, he argued. It cuts off causal connections. What is inside cannot influence what is outside. Susskind's position was strong in its faith in quantum mechanics. If information is lost, the law of energy conservation is violated, and that is impossible. Susskind began searching for a loophole. He needed to understand how information could simultaneously fall in, as the falling astronaut sees, and remain outside, to fly away with the radiation. This seemed impossible. Information cannot be in two places at once. This is called the no-cloning theorem in quantum mechanics. You cannot make a perfect copy of a quantum state. It is either here or there. If the astronaut carried the book inside, it is inside. If the radiation carried the book's information outside, it is outside. If both are true, we have two copies of the book, a photocopy of reality. This is forbidden. Susskind tormented himself with this paradox for years. And one day, an idea came to him that seemed even crazier than the disappearance of information. He called it horizon complementarity. The idea was this: what if the contradiction exists only in our heads, but not in a physical experiment? To detect the paradox, the two copies of the book, someone would need to see both copies. One observer outside sees the book burn up at the horizon. The information flies away. The other observer falls in with the book. Can these two observers meet and compare notes? Hey, I have the book. No, I have the book. No. The meeting is impossible. The one inside cannot send a signal out. The one outside dare not jump in. And if they jump in, they will not catch the first observer and relay the message before both are crushed by the singularity. Susskind proposed, there is no contradiction in nature because there is no single observer who could witness the law's violation. Reality depends on who you ask. For the external world, information never crosses the horizon. For the internal world, it does. And these are not two different copies. It is the same information, described differently. But for this strange logic to work, the very concept of space had to be rethought. It had to be conceded that the three-dimensional volume of a black hole and its two-dimensional surface was somehow the same thing. Thus was born the concept that today lays claim to being the master theory of the universe's structure, the holographic principle. The word hologram, for most of us, is associated with security stickers on credit cards or Princess Leia from Star Wars. But in physics, the concept has a much deeper and more mathematical meaning. Let's return to the problem of a black hole's capacity. Recall Jacob Bekenstein from the third section. He said that entropy, the amount of information, is proportional to the surface area, not the volume. This is very strange. Imagine packing a suitcase. The larger the suitcase, the more items fit inside. Volume grows as the cube of the size, length multiplied by width, multiplied by height. But a black hole does not behave like a suitcase. It behaves like a computer screen. The amount of information a monitor can display depends on the number of pixels. Pixels are on the screen's surface. The monitor's depth does not matter. Susskind and 't Hooft realized that this is a fundamental property of gravity. The maximum amount of information that can be placed in any region of space is determined by the area of that region's boundary. Imagine a library. We usually think the information is contained in the books on the shelves inside the building. The holographic principle asserts, no, all the information about every letter in every book can be recorded on the walls of the library, pixel by pixel, plank length by plank length. If this is true, falling into a black hole looks completely different. When an object approaches the horizon from the external observer's point of view, it is flattened. It is smeared across the surface. Its information, its quantum data, becomes part of the two-dimensional sphere surrounding the hole, like a sticker on a suitcase. The object has not vanished. It has simply transitioned to another form of recording. It has become a two-dimensional code on the boundary. And then, when Hawking radiation flies out of the hole, it reads this code. It takes the data from the surface and carries it back into space. It is as if you burned the library, but the smoke from the fire formed the letters and words of the lost books. Information returns, but in a monstrously encrypted form. This idea that a 3D world, volume, and a 2D world, surface, are equivalent, remained a beautiful hypothesis, almost a philosophy, for a long time. Scientists lacked proof. They needed an example of a universe where this worked with mathematical precision. And such an example was found by the young Argentine physicist Juan Maldacena in 1997. His discovery had the effect of a bombshell. Maldazzina's paper became the most cited work in theoretical physics in recent decades. Maldazzina examined a hypothetical universe. It is not exactly like ours. It has a different geometry, known as anti-de Sitter space, but it serves as a perfect model. He proved a mathematically strict equality. On one side of the equation, a five-dimensional universe where gravity operates and black holes fly, our volume. On the other side, the four-dimensional boundary of that universe where gravity does not exist at all and only quantum fields live, our surface. Maldazzina showed that this is the same physics. Any event inside the volume, for example, the formation of a black hole, has a precise mirror reflection in the processes on the boundary. Gravity in the volume is merely the hologram of quantum effects on the surface. This discovery, known as the ADS/CFT correspondence, was Suskind's triumph. It showed that information truly is not lost, because on the boundary, where there is no gravity and no holes, the laws of quantum mechanics work perfectly. And since they work on the boundary, they work inside too. After all, it is the same thing. In 2004, Stephen Hawking, having analyzed this new data, conceded defeat in the debate. He spoke at a conference in Dublin. Hawking stated, "I was wrong. Information is preserved." He presented John Preskill with the one encyclopedia. It was the Baseball Encyclopedia. A fitting prize, Hawking joked, from which you can retrieve information just as easily as from a black hole. But Suskind's victory has a dizzying consequence for us. If the laws of black hole physics are universal, the holographic principle applies not just to them, it applies to the entire universe. Our universe also has a horizon, the cosmological horizon, the boundary beyond which we cannot look due to the expansion of space. Does this mean that we, you, me, this microphone, the stars outside the window, are all, in reality, two-dimensional information recorded somewhere on the edge of the cosmos? Does this mean that our three-dimensional reality, our sense of depth, volume, and tangibility, is merely a high-quality holographic projection? Many modern physicists believe this is the case. We live inside a giant hologram. Space is not a foundation. Space is an illusion arising from quantum entanglement on a distant screen. We began with the question of why black holes are hot, and we concluded that the very fabric of reality might be structured entirely differently than we perceive. But theory is theory, and physics is an experimental science. Can we touch this radiation? Can we create a black hole in a laboratory and test whether Hawking's formula holds true? It turns out we can. But for this, we do not need a particle collider. We need water, sound, and a bit of liquid light. In the next section, we descend from the heavens to Earth, to the laboratory of the Technion, Israel Institute of Technology, where scientists created a silent hole. Theory is beautiful. The mathematical elegance of Hawking's equations, the holographic principle, the horizon entropy, all of it is mesmerizing. But physics is a stubborn science. It demands proof. It requires experiment. And here we face a gigantic problem. We have already said that real astrophysical black holes are too cold. A hole with the mass of the Sun has a temperature of 60 nanokelvin. This is minuscule. This radiation is so weak that it is drowned out by the noise of the universe's cosmic background radiation, which is billions of times hotter. Trying to catch a Hawking radiation photon from a real black hole is like trying to see the light of a firefly against the backdrop of a stadium searchlight. while standing on a different continent. We will not see it tomorrow or in 100 years. It seemed like an impasse. We were doomed to take Hawking at his word. But in 1981, the same William Unruh who discovered the acceleration effect proposed a brilliant idea. He said, "If we cannot fly to a black hole, let's build a black hole here on Earth." But not from gravity, from sound. Unruh noticed an astonishing similarity between the equations describing light in curved space and the equations describing sound in a moving fluid. Let's use his favorite analogy. Imagine a river flowing faster and faster until it plunges into a waterfall. In this river, live fish, but they are not ordinary fish. They are sound fish. They can swim and propagate a signal only at one fixed speed, the speed of sound. Assume the river upstream is calm. The water speed there is less than the speed of sound. If a fish shouts, the sound can travel against the current and be heard on the bank. But as they approach the waterfall, the current accelerates. At some point, the water speed equals the speed of sound and then exceeds it. Imagine the point where the water flows faster than sound can move. If a fish below this point tries to shout upstream, the sound will fight the current, but the current will still carry it downward into the abyss of the waterfall. The sound wave will paddle desperately, but the bank will recede. This point, where the flow speed equals the speed of sound, is the precise mathematical analogue of the event horizon of a black hole. Only instead of light, we have sound, and instead of gravity, we have accelerating water. Unruh called this an acoustic black hole or a sonic hole, and he predicted that if the equations match, such a hole must also radiate. It should emit not photons, particles of light, but phonons, quanta of sound. The idea lay dormant for almost 30 years. Water is too turbulent a medium. It has too much friction, heat, and noise. Seeing the delicate quantum effect there is impossible. An ideal fluid was needed, a fluid with no friction, where atoms march in lockstep. Such a fluid exists. It is the Bose-Einstein condensate. This is a unique state of matter created by cooling a gas, typically rubidium atoms, to temperatures near absolute zero, fractions of a nanokelvin. In this state, millions of atoms lose their individuality and begin to behave like one giant superatom. They become a quantum wave that can be seen with the naked eye. And then, in 2009, and more convincingly in 2016 and 2019, the Israeli physicist Jeff Steinhauer at the Technion achieved the impossible. Steinhauer created a sonic black hole in his lab. He took a cloud of rubidium atoms, cooled it, trapped it in a magnetic field, and used a laser to make part of that cloud flow at supersonic speed. He created an event horizon mere micrometers in size. And what did he see? In the perfect silence of the vacuum chamber, phonons began to fly out of the event horizon. Most importantly, Steinhauer was able to see what we described in the chapter on virtual particles. He detected correlation. Remember, pairs are born at the horizon. One flies out, the other falls in. They are entangled. They are linked by an invisible thread of destiny. In Steinhauer's experiment, detectors showed precisely this. Click. A phonon flew outward, the analogue of Hawking radiation. And at the exact same moment, click. Its partner was registered inside the supersonic zone, a falling phonon with negative energy. This was the first ever experimental confirmation of the Hawking mechanism. Yes, it is not a gravitational hole. Yes, it is an analog. But the physics behind the process is the same. The quantum field does not care whether it is ripped apart by the curvature of space-time or the acceleration of a flow of rubidium atoms. If a horizon exists, there will be radiation. This discovery caused an uproar in the scientific community. The paper was published in Nature Physics. Many skeptics who had doubted the reality of black hole evaporation for 40 years were forced to concede. The mechanism works. Experiments with analog holes continue. Scientists are now trying to simulate the early universe with them. In laboratory settings, in a tube of cold gas, they recreate conditions that may have prevailed in the first moments after the Big Bang. This gives us incredible hope. We cannot fly to a black hole, but we can domesticate its ghost in a test tube. And that ghost tells us Stephen Hawking was right. The vacuum truly can boil. Now, with both the flawless theory and experimental confirmation of the mechanism in hand, we can confidently look into the future. We can write the biography of the black hole down to its very last line, and that finale will be explosive. Our long journey is nearing its end. We have covered immense ground. We started with the classical 18th century ideas of dark stars, passed through the Einsteinian revolution, witnessed the intellectual duel between Stephen Hawking and Jacob Bekenstein, dove into the quantum chaos of virtual particles, and even saw how sound waves in a laboratory mimic an event horizon. We have understood how heat is born from cold, how information balances on the brink of erasure, and why the vacuum is not truly empty. Now, only the final step remains, the most important and perhaps the most frightening. We must fast forward the film of time not by 100 years, not by 1,000, or even 1 billion. We must travel to the epoch cosmologists call the era of black hole decay. To understand the finale of the black hole's biography, we must imagine the stage on which this finale will play out. Forget the night sky you see now. Forget the Milky Way, the Andromeda Nebula, and the bright clusters of galaxies. All of that is just a brief, instantaneous spark in the history of creation. We are transporting ourselves to a future separated from us by 10 to the 40 years. Try to grasp that number. A 1 followed by 40 zeros. If every atom in our observable universe were a second, their sum would still be less than this time interval. By this point, the universe will be unrecognizable. The age of stars ended long ago. The last red dwarfs, the most economical and long-lived stars, fizzled out trillions of years ago, turning into cooling black dwarfs. Galaxies, as we know them, have ceased to exist. Gravitational interactions have flung most of the dead stars into the intergalactic void, while the rest have fallen into the center to feed supermassive black holes. Moreover, according to some grand unified theories, another catastrophic event may occur by this time: proton decay. The matter that makes up you and me, the planets, the asteroids, and the interstellar dust is unstable. Protons and neutrons will decay into positrons and gamma rays. Solid matter will vanish. The universe will become an incredibly empty, dark, and cold place. The space temperature will drop so close to absolute zero that the difference will be practically indiscernible. The energy density will approach zero. And in this absolute maddening emptiness, only they will remain: black holes. They will be the last custodians of complex structure in a dying world, vast, majestic, spinning in the darkness. The supermassive black holes that were once the centers of galaxies will now drift alone, separated by distances that light will take billions of years to cross. It is precisely then, when the last external light source has extinguished, when the last matter to be absorbed has disappeared, that the black hole's countdown will begin. For billions and trillions of years, they were silent. As long as the cosmic background radiation temperature was higher than their own, they absorbed photons from the cosmos. They grew. They were in thermodynamic equilibrium with a universe that was, by their standards, hot. But the universe is expanding. Expansion stretches the CMB waves, making them colder. And at some point, a moment unique to each black hole depending on its mass, the tipping point is reached. The cosmos's temperature falls below the temperature of the event horizon. The thermodynamic arrow flips. The black hole is now hotter than its environment. And like any hot object in a cold room, it begins to give off heat. The great evaporation begins. At first, it happens unimaginably slowly. Let us look at the numbers to feel the scale. Take a typical supermassive black hole with a mass of 1 billion solar masses. Its temperature is about 10 to the minus 18 Kelvin. This is such a negligible temperature that the black hole will emit only a single photon with a colossal wavelength every few years, or even less frequently. The mass loss will proceed in grams, a gram per century, a gram per millennium. Considering the hole's mass is billions of suns, and the sun's mass is 2 times 10 to the 30 kilograms, it seems this process will never move off the starting line. The time required for such a hole to fully evaporate is described by the number 10 to the 100 years. This number is called a googol. It is a symbol of eternity that nonetheless has an end. Imagine an hourglass with more grains of sand than atoms on Earth, and 1 grain falls once every billion years. That is the rate at which the giants will die. But time is irrelevant when you have eternity in reserve. Eons pass. The black hole slowly but surely shrinks. And here the paradox of negative heat capacity, which we discussed in the 7th section, kicks in. This is a devilish feedback mechanism. The more energy the hole loses, the smaller its mass becomes. The smaller the mass, the smaller the radius of the event horizon. The smaller the radius, the sharper the curvature of space at the boundary. The sharper the curvature, the more powerfully it rips apart virtual pairs in the vacuum, and the higher the temperature. The black hole heats up. At first, this heating is imperceptible, but when the hole's mass decreases to the size of, say, the Moon or a large asteroid, the process begins to accelerate. The temperature rises to values familiar to us. Imagine the moment when a black hole heats up to 20 degrees Celsius, room temperature. At this point, it ceases to be perfectly black in the visible spectrum. Though it does not reflect light, if you shone a flashlight on it, you would not see the beam. If you could touch it, which you absolutely should not due to tidal forces, it would be warm. But it does not stop there. It continues to shrink and heat. 300 degrees, 1,000 degrees. The black hole begins to glow with a dull red light, like coals in a fire. In the absolutely dark universe of the future, ghostly red points appear. 6,000 degrees. Now it glows bright white, like our sun, but its size is minuscule, smaller than a grain of sand. It is a microscopic, yet incredibly heavy, star. 1,000,000 degrees. It shines in the X-ray range. 1 billion degrees. gamma radiation. And here, a qualitative leap occurs. Up to this point, the black hole was cold enough to only create massless particles from the vacuum, photons, light particles, and perhaps gravitons, gravity particles. They have no rest mass, so they are cheap to create. Very little energy is needed. But when the temperature reaches billions of degrees, the temperature inside a supernova explosion, the energy of the Hawking radiation quanta becomes sufficient to create matter. Recall Einstein's formula E equals mc squared. Energy can be converted into mass. The vacuum around the black hole begins to genuinely boil. Not only rays of light, but massive particles begin to fly out of it. Electrons and positrons, neutrinos. The black hole turns into a universal matter factory. It returns to the universe what seemed to have disappeared forever during proton decay. It spits out leptons, quarks, and gluons. It is an incredible sight. A tiny point in space, smaller than an atomic nucleus, operates as the most powerful particle accelerator in history, scattering streams of antimatter and matter around it. And the faster it ejects energy, the faster it loses mass. The death spiral tightens. The process transitions into an explosive phase. The last few thousand years of a black hole's life are an agony. The final hours are madness. The final seconds are a catastrophe. Let us slow down time and look at the very last second of a black hole's life. By the beginning of this second, the hole's mass is approximately 200 tons. That is the weight of a small blue whale or several train cars. But all this mass is packed into a volume billions of times smaller than a proton. In that one final second, all the remaining mass, all 200 tons, is entirely converted into pure energy and radiation. The power of this explosion is colossal. If you convert 200 tons of mass into energy using Einstein's formula, you get an explosion equivalent to the detonation of millions of hydrogen bombs simultaneously. Imagine, in a dead, quiet, absolutely dark universe, where nothing has happened for trillions of years, a supernova-scale flash of light, microscopic in size, suddenly ignites. A fierce gamma ray burst pierces space, flying outward for millions of light years. But the most interesting thing happens in the very last fraction of a second, in 1/10,000,000th of a nanosecond. At this moment, the hole's mass becomes comparable to the Planck mass, about 20 micrograms, the weight of a dust mote, and its radius becomes equal to the Planck length, 10 to the negative 35th meters. Here, at this point, physics as we know it ends. Here, Einstein's general relativity, which has guided us all this time, says, "I wash my hands. I work no further." The curvature of space becomes infinite. The quantum fluctuations of space-time become so wild that the concepts of up, down, before, and after lose meaning. What happens at this singular moment? Stephen Hawking believed the whole simply vanishes. Pop, and nothing is left. All mass transitioned into radiation. Space smooths out, and only the spreading light remains. However, modern theories such as loop quantum gravity or string theory offer other possibilities. Perhaps the evaporation halts. Perhaps a tiny, indestructible object, a relic, a Planckian, remains, a kind of diamond of memory that cannot be destroyed. If so, all the space of the future universe will be filled with this invisible dust of black hole remnants. Or perhaps, at this moment, a passage to another universe opens. Maybe this explosion gives birth to a baby universe that inflates in its own dimension. We do not know. We need a theory of quantum gravity to peer beyond this curtain. But let us return to the radiation left after the explosion. Remember our discussion about information and holograms. In the 10th section, we said that information does not vanish. It is merely re-encoded. Here it is. This cloud of radiation, chaotic, hot, spreading at the speed of light. It contains everything encrypted within it. It holds the information about the star that collapsed billions of years ago. It holds the information about the planets that star-warmed. It holds the atoms of your body, or their quantum description, if you were careless enough to fall into that hole. In his later years, Stephen Hawking came to a conclusion called black hole soft hair. He proposed that the event horizon stores imprints of everything that passed through it in the form of microscopic shifts in space-time. And as the hole evaporates, this soft hair transmits the information to the escaping particles. So, in the very end, when the last black hole explodes in its final fireworks display, the universe will become whole again. All information will return, but it will be scrambled beyond recognition. It will be chaos, heat death in its absolute manifestation, maximal entropy, a state where nothing interesting will ever happen again. Stephen Hawking did not live to see the day we could witness a black hole evaporate. He passed away on March 14th, 2018. His ashes rest at Westminster Abbey. If you ever find yourself there, look for his memorial. It lies between the tombs of Isaac Newton and Charles Darwin. On the dark stone, there is no portrait. There is no list of his awards. There is a formula carved into it, the very formula he derived in 1974, sitting in his chair in Cambridge, deprived of the ability to move, but free in his thoughts. T equals H bar C, cubed divided by 8 pi g m k b. In this short line of symbols is contained the entire drama of the life and death of black holes. The Planck's constant is responsible for the quantum world of particles. The G, Newton's constant, is responsible for gravity and the curvature of space. The C, speed of light, reminds us of relativity. The Kb, Boltzmann's constant, brings in thermodynamics and heat. This equation is a bridge between the world of atoms and the world of stars, between the beginning and the end. It tells us that the universe is unified, that physics cannot be separated into quantum and classical, and that even the most terrifying, darkest, and irreversible objects in nature, black holes, actually obey the laws of heat and light. We began our story with a frightening question. Why are black holes hot? And the answer turned out to be surprisingly poetic. They are hot because they are not perfect killers. They are converters. They are part of the great cycle of energy. Black holes take the chaos of matter, compress it, store it for unthinkable eons, and then, in their dying gasp, return everything back as pure light. The death of a black hole is an act of creation, radiation. Perhaps we and our entire world are also part of such a process. Remember the holographic principle. Maybe our universe is merely a three-dimensional projection on the event horizon of some inconceivably huge black hole in another dimension. And our universe's expansion is just the growth of that hole, or conversely, its evaporation. We are humans, beings living less than 100 years on a small piece of rock near a mundane star. We are made of soft matter that is easily destroyed, but our minds have managed to reach the event horizon. We have managed to calculate the temperature of non-existence. We have managed to predict the fate of the universe across a Google of years. Hawking radiation teaches us one important thing. There are no absolute dead ends in physics. The event horizon is not a wall. Information does not vanish without a trace. Even from the deepest hole, there is a way out if you are willing to wait long enough, or if you are willing to transform into pure energy. As Stephen Hawking himself often liked to say, black holes are not as black as they are painted. They are not the eternal prisons they were once believed to be. There is an exit from them, both outward and possibly into another universe. Therefore, if you feel you have fallen into a black hole, do not give up. There is a way out. And on that optimistic note, we conclude our story about the paradox of the hot vacuum, the story of how one simple formula made emptiness glow. If you feel your eyelids growing heavy, allow the grand story of life on Earth to wrap around you gently and guide you into calm. Don't forget to subscribe to listen to more of our bedtime stories. Close your eyes, take a deep breath, and slowly drift into sleep, into silence, into the boundless, timeless current where all life intertwines. Wishing you a quiet, comforting night.